analytic solution, AI, is what is the greatest height reached by the first rock? We can start out with our average velocity, which is delta z over delta t. And what we're looking for is delta z, the maximum height reached. Well, we don't know the delta t. We don't know the average velocity, so we can use our second average velocity, v plus v0 over 2. And our final velocity is 0 at the top. The velocity is 0, and initially it's 24 over 2, which gives us 12 meters per second. Aha! So now we have an average velocity of 12 meters per second, but again, we still don't know the time. We've already filled out our average velocity table. We go to our third step, which is v equals at plus v0. So we know at the top it'll be 0, acceleration is minus 10, and the initial velocity is 24. So 10t equals 24, t equals 2.4 seconds. So 12 times 2.4 is 28.8 meters. With two significant digits, then delta z would be 29 meters. So that's AI. BII, how long does it take to reach its maximum height? Well, we've already figured that out. That's 2.4 seconds. How long does it take to return to the same height? Well, we could use our table to get a clue on this, but the same height would be when we were at 0. And so we get to 0 here between 4 and 5 seconds. Well, 4 and 5 seconds, we know we could say conceptually, it's actually just twice as long as this. So it's 2 times 2.4 seconds. Time up equals the time down. So that's one way we could get at that. So 4.8 seconds. The other way we could do this is look at the table and see that it's got to be between 4 and 5. The delta z is going to be 0 when it's the same height, and that's going to be pretty close to 5 seconds. And that's what we see with 4.8 seconds. We could also say, because of symmetry, we know that the velocity, when it reaches the same height on the way down, will have the velocity in the opposite direction. So we want to know when it has minus 24. So we have minus 10t equals minus 48. So t is 4.8 seconds. So there's a bunch of ways we could get at A3. A4, how long does it take to reach the base of the cliff? Well, we have two equations for this type of thing. V equals at plus v0 and z equals 1/2 at squared plus v0t plus z0. Now we set the 0 to be the initial position to be 0. So, and we want to know when it reaches the ground, which is minus 120. So we have 1/2 times minus 10 t squared plus 24t, and the initial position is 0. So we want to know when minus 20 equals minus 5t squared plus 24t. Now we could put this into our graphing calculators, and we could set y1 equal to minus 5x squared plus 24x. And y2 we can set equal to minus 120. And we can calculate an intersection. And that value turns out to be, when we do that, 7.85 seconds, which to two significant digits is 7.9 seconds. Now, if we go to our average velocity table, and we look for minus 120, that's in here, and that's between 7 and 8 seconds. So our answer does agree with the average velocity table. And what will the impact velocity be? Well, we'll use the v equals at plus v naught. Minus 10 times 7.85 plus 24 is minus 78.5 plus 24, which is minus 54.5, or minus 55 meters per second. And if we look at the table, we said that height of minus 120 will be attained at this time, and that's between minus 46 and minus 56, and we said it would be pretty close, because 120 is pretty close to 128, and sure enough, we get minus 55. So that's A5. Now moving on to B. BI. So how long does it take the second rock to reach the ground? Well, from our table, we see that it takes between 3 and 4 seconds. Should be the answer. But we could go about this the same way with our z equals 1/2 at squared plus v0t plus z0. We want to know when the position is minus 120. The acceleration is minus 10. We're looking for the time. The velocity is minus 24, and the starting position 0. So we have minus 120 is minus 5t squared minus 24t, which you will notice looks exactly the same as our other equation here, except that this sign is different. So we can go back to our calculator, and we could put y1 is, all we need to do is change the plus 24 to minus 24. Y2 remains the same at minus 20. We calculate an intersection, and we find out that t is equal to 3.05 seconds, or the t is 3.1 seconds. And if we go back to our table, we said it was between 3 and 4 seconds. We said it would be very close to 3, and indeed it is. So 3.1 seconds. What will its impact velocity be? Well, we can do v equals at plus v0. We want to know the impact velocity when the acceleration is minus 10 after 3.05 seconds when the initial velocity is minus 24. So that's minus 30.5 minus 24, which is minus 54.5 meters per second, which to two significant digits is minus 55 meters per second. And we then see that that is exactly the same as the velocity when it's thrown upward. And of course that should be the case because this velocity, if it's plus 24, when it gets back down, it's minus 24. Well, that is the speed at which the second rock was thrown downward. So they both, from this moment in time, have exactly the same initial velocity. That also tells us this is the time for the first rock to hit the ground after it's returned to the same height. So we had 2.4 seconds up, plus 2.4 seconds down, plus the rest of the way down, which is 3.05 seconds, which gives us 4.8 plus 3.05, which is 7.85 seconds. And you notice that is the time that we got for it to fall the entire distance from the beginning. So CI question is, what conditions would we change for them to hit the ground at the same time? Now, the perplexing thing was that the one we threw second actually hit the ground first. Well, the difference is, since the first rock (2.4, 2.4, and 3.05. And the first one is 3.05. So we want them to hit the ground at the same time. We need to throw the first rock, or the second rock, after 4.8 seconds. So, for impact time to be the same, the second rock should be thrown after 4.8 seconds. Now that is the statement of the answer. The explanation of why is that the behavior of the second rock, velocity and delta c, is the same as the first rock after it returns to the same height. Both have a downward velocity of minus 24 meters per second at the release height, and therefore will take the same time to hit the ground. After 4.8 seconds, the first rock will be in exactly the same, be at this exactly the same height as the second rock.